So the talk today will be structured like follows. First, I will give you the definition of first-order differential calculi over, in general, non-commutative algebras. Then I will talk about covariant first-order differential calculi, and in particular, I will mention Voronovich's result classifying such covariant calculi. And then we will generalize to higher order differential calculi and mention the maximal prolongation. And then we will get to the definition of an almost complex structure and a complex structure for a star differential calculus. So to start, the definition of a first-order differential calculus, gamma d is the information over an algebra that is unital and associative, is the information of an A bimodule gamma, which means I can act from the left and from the right with A on gamma. A map that is k-linear from the algebra to the bimodule, satisfying the Leibniz rule, called the differential, and a surjectivity condition, which means that any element of the calculus can be written in the form A dB for some A and B in the algebra. For example, we can think about differential geometry as some motivation for this definition. You can take M as smooth manifolds, a smooth manifold, and consider the algebra of smooth functions on it, C infinity of M. Then you will have that the space of differential one forms, which is the space of sections of the cotangent bundle, together with the exterior derivative, is a first-order differential calculus on C infinity of M. In this case, you have that the bimodule structure is defined like so at each point P in the manifold. So the one form omega acted upon from the left by a smooth function f at the point P coincides with f acting from the right on omega. And this is not the case in general for non-commutative, for the non-commutative case. Another example, and this is an important one, of first-order differential calculus over a K-algebra A is that of the universal first-order differential calculus, where taking gamma u, the kernel of the multiplication map inside A, and du, this map here, sending A into 1 tensor A minus A tensor 1, where 1 is the unit of A, you can prove that this is a first-order differential calculus. In fact, the kernel of the multiplication has an A bimodule structure by just multiplying from the left the first tensor factor as a left action and as a right action multiplying from the right the second tensor factor. This will still be in the kernel of the multiplication. And du satisfies the Leibniz rule. Here is a quick proof, and also lands in the kernel of the multiplication. And the surjectivity condition is met. So any A tensor B in the kernel of the multiplication can be written as A du B. And there's this theorem by Voronovich, which tells you that any first-order differential calculus on a K-algebra A can be obtained as the quotient of the universal one. So there is a surjective map pi such that gamma is isomorphic to gamma u modulo n for some A sub bimodule n of the kernel of the multiplication. This as A bimodules, and moreover, you can obtain the arbitrary differential d as the composition of pi with the universal first-order differential calculus differential. And okay, now we go to covariant first-order differential calculi. And here we fix A comodule algebra, and H comodule algebra really, where H is an Hopf algebra, which means a B algebra with an antipode satisfying some compatibility conditions with the algebra and coalgebra structures. And A is not only an algebra, but also a comodule. So there is a left, in this case, coaction of H onto A, which means there is this map here from A to H tensor A. And comodule algebra means that this is behaving well with respect to the algebra structure of A. And when you consider first-order differential calculi over comodule algebras, you can think of covariant first-order differential calculi, which are defined like so. So when gamma is a first-order differential calculus, gamma D is a first-order differential calculus over a left A comodular algebra A, you can say that gamma is a covariant, left H covariant first-order differential calculus if gamma is not only an A bimodule, but also an H comodule, meaning there is a well-defined left H coaction on gamma. And the differential is a morphism of comodules. So somehow you have lifted, which is precisely the fact that this diagram commutes, the fact that this is a morphism of comodules. So you have lifted the structure of comodules of A to the level of the calculus. And you can do the same definition for right covariant first-order differential calculi. Now, if we take A to be H itself, we can view any Hopf algebra H as both a left and a right comodular algebra just by considering its coproduct as a left and a right coaction. So you can consider covariant calculi over algebras, first-order covariant calculi over Hopf algebras, when this diagram and this diagram commute, and there is well-defined left and right coactions on gamma. And there is a theorem by Voronovics again, which tells you that there is a correspondence between right ideals inside the kernel of the counit of H, which we denote by H+, and left covariant first-order differential calculi over the Hopf algebra H. Moreover, when you have an ideal that is also invariant with respect to this adjoint right coaction on the Hopf algebra H, you will end up with a bicovariant first-order differential calculus and also the other way around. So to give you an idea of the proof, so starting from a right ideal, you obtain a left covariant calculus defined like this, so H tensor H plus mod I, and you have a differential like this, so where pi here is the projection map from H plus to the quotient H plus mod I. You can prove this has a well-defined left coaction, and that when this is also invariant with respect to the adjoint coaction, that this is a well-defined right coaction, and the differential is a morphism of comodules. The other way around, you start from a left covariant first-order differential calculus, and then you will get a right ideal inside the counit as the kernel of this map, which is usually called the quantum Mauré-Cartan form, which is proven to be surjective onto the left coinvariant forms of the calculus. And now you can use the fact that the calculus, since you started with the left covariant one, is a left Hopf module, and thus you get that gamma is isomorphic to H tensor H plus mod I, since H plus mod I is isomorphic to this, because I is the kernel of var pi and var pi is surjective. So there is this correspondence by this result. And then we go to higher order differential calculi. The definition of a differential calculus in general, so an higher order one, on a K algebra A is a differential graded algebra, omega bullet D wedge, generated in degree 0, meaning that the 0 degree forms are the algebra itself, and every K form can be written as a linear combination of these guys. And in particular, what this means is that omega bullet wedge is a graded algebra, omega bullet D is a complex, and then wedge becomes a morphism of complexes, and this results in this graded Leibniz rule. For example, we can take this, which is called the universal differential calculus, and you take as a graded vector space the direct sum of these guys omega un, which are defined as the intersection from k that goes from 1 to n of these mu k multiplications maps, which multiply the kth and the kth plus 1 tensor factor of the tensor factor of A with itself n plus 1 times. You take all the kernels for all k's from 1 to n, you intersect them, and you get a graded vector space. and you can define a differential on it like this, and you can quickly check that this is the first order differential, universal differential calculus differential for like when I just take it on an element of A. This will result in two terms. So I goes from 0 to 1, and you get 1 tensor A minus A tensor 1. Because you're substituting 1 in the ith position. And then the wedge product is just concatenation, where you multiply the last element of the K form omega, last tensor factor of the K form omega with the first tensor factor of the L form eta, and you get a K plus L form. Now we get to the maximal prolongation. So you can have any first order differential calculus over an algebra A, and you can prolong it to a differential calculus on it by this construction. So we know by Voronovich's result that any first order differential calculus is as an A bimodule the quotient of the universal first order differential calculus by n, some A sub bimodule of the kernel of the multiplication. Then we can take the tensor algebra, which is this. So the direct sum of A, which is the degree 0, the first order differential calculus, and then the balanced tensor product over A of the first order differential calculus with itself, and so on. And you can define a two-sided ideal of this tensor algebra by taking the image of the A sub bimodule n under this map, d squared, which takes an A tensor B in the kernel of the multiplication and sends it to dA tensor A dB. And you can prove that you have a differential calculus by taking as a graded vector space the quotient of the tensor algebra by this two-sided ideal, and there's a differential, this one. And the wedge is just the balanced tensor product, but now you're tensoring quotiented elements. And this is called the maximal prolongation of the first order differential calculus gamma. You can prove that the universal differential calculus we have seen earlier is the maximal prolongation of the universal first order differential calculus, and it coincides with the tensor algebra of the first order differential calculus. So you're quotienting by nothing because there is no n sub bimodule corresponding to the universal first order differential calculus. Then you can also prove that the maximal prolongation of any first order differential calculus is the quotient of the universal differential calculus, mimicking what we have seen in the first order case. And then interestingly, if you have any differential calculus omega bullet d tilde wedge tilde extending a first order differential calculus gamma d, meaning that the one forms coincide with gamma and the differential d tilde restricted to A is d, then this will be the quotient of the a quotient of the maximal prolongation of gamma d. Now we get to the definition of a complex structure. And for this, we need the notion of a star differential calculus over a star algebra. And this is just a differential calculus omega bullet d wedge, such that the star involution operation on A is lifted at the level of the differential calculus like so. So d omega star is d omega star for every omega inside big omega bullet. And there is this compatibility with the wedge multiplication where the star gives you a -1 factor to the degree of omega, degree of eta. And it's anti-multiplicative. And just to mention it, if you have a first order differential calculus, which is a star calculus, which means there is this compatibility, then you can take the maximal prolongation, and this will be, again, a star differential calculus. Now, the definition of an almost complex structure for a star differential calculus, omega bullet d wedge, is having an n0 grading for omega bullet. So you can write omega bullet as the direct sum over all AB in n0 squared of omega AB. And you have to have that the K forms are the direct sum of all B forms in omega AB, such that the sum of AB is K. and that the star of an ABB form is a BA form. So now you can consider two operators which are defined on an AB form like so. So you take the total differential on AB, and then you project, since D is a degree 1 map, you project the omega A plus B plus 1 forms into just the omega, into the A plus 1 B forms. And here you do the same, but you project to the A B plus 1 B forms. And the definition of a complex structure then for a star differential calculus, which has an almost complex structure, is that the differential splits, the total differential exactly splits into these two operators, partial and bar partial. And equivalently, this you can prove is not part of the definition. You can prove that this is equivalent to having that partial squared is 0, bar partial squared is 0, and that D on the 1, 0 forms is contained inside the 2, 0 plus the 1, 1s, and the 0, 1s on the 0, 1s is 1, 1 plus 0, 2. And yeah.
Also ask that the wedge product respects this A and B grading. So like if you have like just an A comma 0 form and A prime comma 0 form, do you ask that the wedge product of them is like an A plus A prime 0 form?
Makes sense. I think so, but I did not mention it. Yes,
it should be an N2 algebra grading on the first line, and almost
okay.
on the star differential calculus is an N2 algebra grading.
N2 algebra grading. I don't know what it means, but
it means exactly what Thomas said. So
okay,
when I have
okay.
two forms, I have an AB form. And I multiply them, I go to A plus AB and A prime.
Yeah.
It goes into A plus A prime and B plus B prime.
Okay, good. Also, okay, and I'm finished. This thing here is equivalent to saying that this with partial and bar partial is a double complex, which means that partial and bar partial square to 0, and the composition of the two is minus the composition in the reversed order. That's it.
Of the maximal prolongation of the universal. One of them, the tensor algebra, is very easy and nice, and the other one is complicated. What's the advantage of the other one?
I don't know, because the other one, it seems like you're defining the same, you have the same structure, you know, you have kernels of the multiplications, you have a differential which makes a 1 appear, and so you see the analogy. I mean, you can take this as a definition, you can prove that this is a differential calculus, and then you can show that the maximal prolongation of the universal coincides with this. Yeah.
I may have seen this during my PhD, but I forgot.
Yeah, I know. I
mean, this is actually, so if you think about it, it's not so complicated, because like if you take the tensor algebra of like omega 1 universal with itself many times and tensor A, then of course you can collapse just the middle factors, and what this means is that every nearest neighbors you multiply, you should get 0. And yeah, that's what's written here.
So I have a question.
Yeah, go ahead.
Yeah. But for this example of the universal differential calculus of AE, so what is the universal property? Because for the next slide, you have a universal property, but what is the universal property for this?
Because the projection map is unique, I think, is the answer. So from like the maximal prolongation of the first order universal, so the universal differential calculus to any other maximal prolongation, and then to any other calculus extending the same first order calculus, is unique, I think, the projection map. So this is why it is called universal. So
Okay.
a projection of differential graded algebras, and then I don't know, maybe you can answer better. Yeah, it's the same as for the first order differential calculus.
Well, for the general maximal prolongation, it's the same. It's because they're isomorphic.
Thank you.
Further questions? If not, then let us thank Giovanni again. And then we will take a break until 4 for the main seminar.